In today's lab experiment, we're going to investigate the relationship between the volume and the temperature of a gas in a container. What we're going to do is vary the temperature, and then we're going to observe the volume. So that makes the temperature the independent variable, that's plotted on the horizontal axis, and volume is the dependent variable, and that's plotted on the vertical axis. We've already seen that the volume of a gas is affected by the pressure, so we'll have to control for pressure. This is pretty easy to do if we confine our work to less than an hour or two, because the atmospheric pressure rarely changes much in a short period of time. If you've ever blown up a balloon, you know that adding particles of air to the balloon changes its volume. So we'll have to control for number of particles as well by making sure that this doesn't change while we measure the volumes. Also, this is pretty easy to do if we just make sure that the gas stays sealed inside the container. We're going to use a glass tube that's sealed at one end as part of our container of gas. If you look at this picture here, this is a photograph of our apparatus. The end of this glass tube is sealed, and so gas can't get out of there. The gas that we're using is just air. On the other end, we're going to have an oil plug. So if you look farther up this tube, you can see there's a little, what looks like a blank spot, looks like a bubble of oil. That bubble of oil traps inside of the tube a volume of air that's our gas. Now, the other thing that's inside here next to it is an ordinary thermometer. And that thermometer is going to be what we use to measure the temperature as we watch the volume change. So we're not actually measuring volume, we're actually measuring the height of the column, but that's proportional to the volume because the volume's diameter is constant inside this tube. Also, we're not actually directly measuring the temperature of the air inside that bubble because our thermometer isn't really inside there. But it does measure the temperature of some water that this is all going to be immersed in, and that water will be about the same temperature as the temperature of the air. So we're indirectly measuring that temperature. What we'll do is we'll fill this beaker up with a water bath that's very hot, and then we're going to let it cool down, and as it cools down, the air temperature will cool down. Every 5 degrees of temperature change, we'll take the temperature, we'll measure the temperature, and we'll also measure the volume. When this experiment was done with the temperature of the water bath starting at 95 degrees Celsius and cooling down to 25 degrees Celsius, we got this result. The fact that the correlation number on the linear fit is really close to 1 tells me that a line is a good model for this relationship. If the volume of a gas is maintained by the collisions of particles pushing on that oil plug, and if the particles slow down when the temperature gets lower, it would make some sense that there would be almost no volume when the temperature is as low as it can be, because that means that the particles aren't moving at all, and they can't push the plug to any height. However, we have a vertical intercept that's not exactly 0. Is it reasonable to throw it out? The general rule is that if your vertical intercept is less than 5% of the largest value on the vertical axis, you can throw it out if it makes logical sense. The highest value of volume is about 120 millimeters. 5% of that would be around 6 millimeters, and our vertical intercept is way more than 6 millimeters. So it's not reasonable to throw that out and round to 0. Now, scientists knew there was something wrong with this situation because of the logic that I just described. So they quickly realized that the problem is that 0 degrees C is not actually 0 in terms of temperature. As everyone who lives in the north knows, it's totally possible for the temperature to be negative. So the temperature when the particles have stopped moving, which would be the coldest possible temperature that there is, it's not really 0 degrees Celsius, but it's some negative temperature in the Celsius scale. Now, we could just leave this model with a vertical intercept, but that's kind of a hassle in a model. And so scientists were interested in finding out what is that coldest possible temperature and then making a temperature scale that starts there. Now, we can do this by just expanding the graph and finding out what is the temperature when the volume actually does reach 0. In this graph, what we've done is taken our graph and we just stretched it out. You can see that the points are still up in the upper right-hand corner from our experiment, but now we've just extended that best fit line down to where the volume is 0. And you can see that it's much less than 250 degrees Celsius. It's 258 degrees below 0. When scientists did this over and over again and took very careful measurements and kind of combined all of their data, they found that absolute zero is best approximated by negative 273.15 degrees Celsius. So they invented a new temperature scale called the Kelvin scale. A degree on the Kelvin scale is the same size as a degree on the Celsius scale. It just starts at absolute zero. So to convert any temperature from Celsius into Kelvin, you just add 273. Technically, you'd have to add 273.15, but 273 would be close enough for most of our calculations. Now, the actual slope value on our line here is specific to our particular temperature and pressure that we are operating under, so it's probably not useful for predicting the behavior of other systems. But we can still draw a conclusion. The conclusion is that a straight line is a good model for how the volume changes when the temperature changes. That straight line has no vertical intercept as long as you're using an absolute temperature scale like Kelvins. So V equals KT is a mathematical model that describes this relationship. If we divide both sides by temperature, we can get a form of this equation that I think is more useful in understanding how these two variables are related. Because V divided by T has to remain constant, whatever happens to one of the two variables, the same thing has to happen to the other variable in order to keep that value constant. So if the absolute temperature doubles, let's say, the volume would also have to double in order to keep K constant. If the absolute temperature was cut in half, the volume would also have to be cut in half in order to keep the number constant. Now, it's very important to point out that you have to use absolute temperature, the Kelvin scale, for this model to work. Here's an example of what I'm talking about. You might think that going from 50 degrees C to 100 degrees C doubles the temperature, and so the volume should double. But that's not true. 50 degrees C is 323 kelvins, and 100 degrees C is 373 kelvins. 373 is not double 323. So it's easy to fool yourself if you don't convert your temperatures into kelvins before you use this model. So once again, the conclusion of this experiment is volume and temperature are directly proportional. In other words, whatever happens to absolute temperature, the same thing must happen to the volume in order to keep our constant constant.